In today's lecture, I'm going to talk to you about torque, and we're introducing the subject here. So, first of all, the definition of torque is the tendency of a force to rotate an object about an axis. Torque is a vector. Specifically, in a previous lecture, we covered vector or cross products, and torque is the cross product of the position vector and the force vector. So the result here of the torque is going to be perpendicular to the plane formed by the position and the force vector. So here, in our little sketch, R and F are in the XY plane, and so torque is perpendicular to that in the Z. Now, specifically, the direction of torque can be found via the right-hand rule, which was covered in a previous lecture. But, just to recap, if you take your right hand and you point your fingers in the direction of the position vector, and then rotate your right hand so that the palm moves towards the force vector, then that will give you the direction of torque. So that's one way to do the right-hand rule. I call it stop in the name of love. So you point your fingers along R, rotate your palm towards F, and your thumb is your resultant torque. Now another way I called the gun, okay, so you make a little gun with your fingers. This is vector number 1, this is vector number 2, and this is your resultant. So in that case, you would point your fingers along R, and then your middle finger would point along the direction of F, and yet again your thumb is your resultant vector. So that's the way to do that, and you should practice a lot to get used to it. Sometimes you have to contort your hand in weird ways, which is kind of funny for me to watch when you're taking a test. So the magnitude of the torque can be found a couple of ways. One way is to do that 3x3 determinant for the cross product like we covered in a previous lecture. And then you can also just multiply the magnitude of R times the magnitude of F times the sine of the angle in between R and F. Okay? Okay, so that's two ways there. Now, I have here this equation, torque is equal to RF sine of phi. Here, phi is the angle in between R and F in this sketch. And RF sine of phi, which is equal to F times R perp. This little symbol down here at the bottom indicates the perpendicular. Now, R perp, that's the moment arm or the lever arm, and it's equal to R sine of phi, okay? What it is it's the component of the position vector that's perpendicular to the force, and only components of the position vector perpendicular to the force will have a tendency to create torque. I've got a better sketch of it here, okay? Let's say that you're trying to rotate something like a door, for example. Let's say this is a top-down view of a door. And it's attached about some axis, some rotation axis here indicated by the white circle, okay? Now, let's say that you're exerting a force on the edge of your door here to maybe pull the door closed or something. Okay, so your vector R is going to point from the rotation axis to the point of application of the force. So that shows it here. And then F is sometimes also pointing along what they call the line of action. Sometimes it's called the line of action. And F points along that line there. Okay? Now here, the angle between R and F is shown with theta. And so the magnitude there would be the magnitude of R times the magnitude of F times the sine of theta. But you can also see a sketch of what R perp looks like. R perp is going to be the component of our vector R that's perpendicular to our force. And that's easy to see in this little right triangle drawing here. Okay? And you can find the magnitude of R perp by multiplying R times sine of theta once again. All right? Now, due to that cross product, which causes that sine of theta, or if you do the vector cross product with a 3x3 determinant, you'll be able to see this too. Due to that vector cross product, components that are parallel to the force do not contribute to the torque. So components of R parallel to the force don't contribute to the torque. Or another way to think about it is that if you exert a force and that force isn't perpendicular to your position vector, then only components of force perpendicular to the position vector will contribute to a torque. All right? Now here, the direction of torque yet again can be shown using the right-hand rule, so let's do that together. R cross F gives you the torque. So here, the torque would be pointing out of the screen at you. And remember that out of the screen at you or out of the page is indicated with a dot with a circle around it, whereas into the page would be an X with a circle around it in most textbooks. Now, the horizontal component of the force, it has no tendency to produce that rotation, that F cosine B, F cosine theta. It doesn't produce the rotation. So just remember that. Okay, now, torque has a direction because it's a vector. But oftentimes we just symbolize it with either, whether it causes a clockwise or a counterclockwise rotation. So if a torque or a force has a tendency to cause a counterclockwise rotation, then that's indicated as a positive torque. Remember, counterclockwise angular displacements are also positive, so this is consistent with that. Now, if the tendency of a force is to turn the object clockwise, then usually we pick that as negative torque, okay? Now, torque-based superposition, and that means that if you have a number of forces that have a tendency to exert a torque on an object, then to find the net or total torque, you just sum those up. So, for example, here we have two forces on the object, F1 and F2, indicated by the blue arrows. And it's fixed, this object is fixed or is rotating about this point O here, okay? And so you're going to have one that will give you a counterclockwise torque, and that's from force 1. So that would be plus F1 D1, where D1 is the moment arm or lever arm. And then you have one, this F2, that would have a tendency to rotate it clockwise. So that's going to be a negative torque. And the moment arm for that one is D2. And so the total or net torque would be the sum of those two torques, F1 D1 minus F2 D2. Now that's just a simple example, but it does kind of drive home the point that torque obeys superposition and that the direction of torque could be indicated by a plus or minus sign depending on whether or not it causes a counterclockwise or a clockwise rotation. The units of torque are newtons times meters because it's, R cross F, and the units of F are newtons and the units of R are meters. Now, although torque is a force multiplied by a distance, it's actually really different from work and energy. First of all, work and energy are scalars, and torque is a vector, so that by itself makes it completely different. So we never call the units of torque joules, even though dimensionally they're the same thing. A joule and a newton meter are dimensionally equivalent, but since energy and torque are such different concepts, we never refer to the units of torque in joules. Now, sometimes students get torque and force confused, and they use language which says, I've got a force on the object causing it, so the language gets screwed up sometimes too. So I like to emphasize the differences between torque and force. So first of all, the units aren't the same, okay? The units of force are newtons, and the units of torque are newton meters. So that's different. Now, here's another big difference. Forces don't depend on your choice of origin. So if you have a 3 Newton force that's going east, then regardless of where you put your origin, that 3 Newton force will still be going east, okay? But torques do depend on the origin. They depend specifically on the moment arm. So if the moment arm changes, then your torque is going to be totally different. So for another reason, another example of how torques and forces are different are kind of exemplified by this sketch I've got here below. Here we have 2 wheels, and both of those wheels have the same radius r, and both of these wheels have 2 forces acting on them. All the forces that you see here in the sketches are of equal magnitude, okay? But one of these wheels has a net force of 0, and one of the wheels has a net torque of 0, okay? So let's look at the one on the left. This one has a net force of 2F downward. So let's say that you have this black axle here and you're pulling downward, okay? You're going to have a tendency to try and strain that axle, right? It's being fixed maybe to the wall or something by the axle. It can rotate about the axle, but you're not going to rotate it. You are going to pull it down and strain that axle a little bit. So you will have a net force on that object, and that force will be 2F down. But your net torque here, see, one of these forces, the one on the right, has a tendency to rotate the object clockwise, R cross F, into the screen here, and so that's going to tend to rotate your object clockwise. The other force, R cross F, is in the direction to rotate the torque, or rotate it counterclockwise. And so that's going to be a negative, or I'm sorry, a positive torque counterclockwise, and it's coming out of the screen at you. Okay, so since they're of equal magnitude, though, each of the torques here has a magnitude of RF, but one of them is plus RF and one of them is minus RF. So when you sum them, the net torque is 0. So that means that this object will not rotate. So its net torque is 0 and its net force is 2F down. Now let's look at the one on the right here. Okay, now in this case, it's got an upward force acting on it and a downward force acting on it. They're of equal magnitude, and so the net force on this object will sum to 0. So you're not straining the axle if you push it like that. But in this case, we do have a net torque. Okay, now here you've got, for the force on the right, R cross F, the torque is coming out of the screen. It's going to tend to rotate the object counterclockwise. The torque on the left here, R cross F, torque is coming yet again out of the screen, and yet again it's going to tend to rotate that object counterclockwise. Okay, and so that one, the two torques actually sum, so you have plus RF, which gives you a net torque of plus 2RF. Okay, so in this case the net force is 0, but the net torque is 2RF. All right, let's talk about how you handle torques that are caused by gravity acting on an object. Like here, this little sketch that I borrowed of the Leaning Tower of Pisa here. Okay, this object is going to tend to try to rotate about the base, right? And so you have your position vector pointing from the base of the leaning tower to the center of mass of the object, right? The center of mass is where your gravity is going to act to try to create a torque on that object, all right? So you would have a torque due to gravity for this leaning tower. So I'm going to prove this to you, that the weight of an object can be considered to act at the center of mass. So if the weight is causing a torque, the center of mass is going to be the point of application of that force for your torque calculation. All right, so let's show it here. Let's pretend now that we're going to break up our Leaning Tower of Pisa into little imaginary chunks, okay? We're going to sum over all the chunks, and each one of those little chunks is going to cause some kind of torque, okay? And so you might have a chunk down here at one of the bottom windows, and you'd have a torque due to that chunk, and then you have chunks up here at the top, okay? And that chunk will cause a different torque. So the position vectors are going to point from the base here, where my origin is, to all over the leaning tower, and you would sum over those torques for all these chunks. So I indicate that with the net torque is equal to the sum over all the little chunks torque, tau sub I. Now that tau sub I would be the position vector R sub I crossed with the weight of the chunk, which would be mi times g, okay? So I now have the summation over Ri cross mi g. Now, since m is a mass, it's a scalar, I can move it wherever I like, okay? And so I can move it so that instead of multiplying g, it's multiplying r. Why not? I can do that with scalars. I can put them wherever I like. So here I've got the sum over mi times Ri cross g. All right, now I'd like to remind you of the definition of our center of mass vector, which I've indicated here with R subscript Cm. And that's 1 over the total mass, which I've indicated here by big M, of the sum of all the little mass chunks times their position vectors, sum of mi, Ri. So that's my definition of my center of mass. And so what that means is that this summation of mi, Ri, which I see here in my net torque calculation, that could be written as big M times my position vector RCM, okay? So if I sum all that, then I'm going to have, plug that in, I'm going to have my net torque would be equal to big M times my center of mass vector cross G. And so I could indeed consider this as one position vector that points from the point of origin to the point of application of the force, which is considered to act at the center of mass, okay? So that's my proof there. Let's do an example problem where gravity has a torque and is acting on it. In this, I'm going to highlight statics. So this is a problem in statics. Now, engineering has entire courses on statics, and basically it's a system. Statics are systems that are in equilibrium, which would mean that they have a net force and a net torque for the entire system of 0. Okay? So one such system that would be a static situation would be like a uniform density semicircular rod that has a total mass m, and that's indicated here in this sketch. Now we're going to prop our little semicircular rod so that one end is sitting on the floor and the other end is propped against the wall, okay, as shown. Okay, now we're going to ignore the friction in between the wall and the rod, but we're going to consider all the other forces and then find the values of the normal forces in terms of the object's weight, mg. Okay, so that's the goal here. All right, so let's first consider our free body diagram. Now, if we ignore the friction in between the rod and the wall, then I'm going to have 4 forces to consider. Okay, so first, of course, I have the weight indicated here by W, and the weight, as we just discussed, could be considered to act at the center of mass of the rod. Now, if this is a uniform density rod, then that center of mass will be right here in the middle by symmetry arguments. Okay, so that's where I'm going to draw my weight vector acting. Now, I'm also going to have the normal forces in between the rod and the wall and the rod and the floor. Those I've indicated as N sub W and N sub F for wall and floor here in the drawing. The normal force between the rod and the wall will be pointing straight to the right, okay, because it's always perpendicular to the surface. The normal force is always perpendicular to the surface. Now, the normal force between the rod and the floor is going to be pointing straight up, okay, and I've indicated that down here. Now finally, my last force is the force of friction in between the floor and the rod. Remember, I said I was going to ignore the friction between the wall and the rod, but not the floor. Can't ignore that one and have it sit there, okay? So here I've got the force of friction, and it's going to oppose the direction of motion that the object wants to go. And so since it's going to want to slide away, then the force of friction is going to point in towards the wall, towards the left, okay? So that's my free body diagram. Now, I'm going to write my forces in their vector notation. So N sub W is going to be plus NWI hat. I'm taking my x-axis as being parallel to the floor and to the right as plus x. I'm going to take my y-axis as being parallel to the wall and up as plus y. Okay? So N sub W is equal to plus NWI hat. The normal force from the floor, N sub F, is plus NFJ hat. The weight, W, is minus MGJ hat. And the force of friction is minus F sub F I hat, okay? Now, I've got 2 things that are going to sum to 0. One is the forces, and one is the torques. Let's do the forces first. So, the sum of the forces in the x direction must equal 0. And that's going to be my 2 forces with x components are my normal force from my wall and my force of friction. So, my equation is 0 is equal to N sub W minus F sub F, the normal force for the wall minus friction. Now, my sum of the forces in y is also going to be equal to 0. The 2 forces that act in y are the normal force for the floor and gravity. So 0 is going to equal plus N sub F minus mg. Now, solving these equations, which are actually pretty simple, I get that the normal force from the wall has to equal the magnitude of the force of friction, N sub W equals F sub F. And I also get that the magnitude of the normal force from the floor has to equal the weight, mg. So N sub F equals mg. Well, one of them's done then, because the problem said solve for the normal forces in terms of the weight of the object. So I've done that for my normal force of the floor. But I don't have it quite done yet for the normal force from the wall. Fortunately, I do have another set of equations, because the torques must also sum to 0. So if I sum the torques setting them equal to 0, okay, let's first look at each of these forces and which are going to cause torques and in what direction. Okay, so let's look and consider that the origin will be the intersection right here of the floor and the wall. So that's my origin. So if I look at the normal force from the wall, okay, and I do my vector cross product, then that means that the normal force from the wall is going to have a tendency to rotate the object clockwise. So that's a negative torque. And the magnitude of that torque would be the radius of my circle arc, big R, times N sub W, because my position vector would point straight up, right, from the intersection of the wall and the floor to N sub W, and that's a 90-degree angle there. So I'm just going to have R times N sub W for my magnitude of the torque, and then it's going to be negative for that normal force in the wall. Okay, now let's do the weight. Okay, if you do the cross product here, you've got R pointing from that intersection to the point of application of the force, which is the center of mass. If you do that cross product, you see that that torque is also going to cause a counterclockwise rotation. So this is a negative torque. Now, however, the angle in between the position vector and the force in this case is not 90 degrees. In fact, if you look here, I've sketched it out. This dashed line extends, and then you can see that the weight swings down from that. So that would be a 135-degree angle in between the position vector and the force there. And it's negative, so my term for the torque for weight is going to be minus RMG sine of 135. Okay? All right, now let's look at the normal force from the floor. Okay, this one, the intersection from the wall and the floor to the point of application of the force, in this case, this is going to cause a counterclockwise rotation. Okay, and so that's going to be a positive torque. So the torque magnitude of that torque is R times N at sub F. And that's because, of course, our position vector points along the floor. Our normal force points straight up. That's a 90-degree angle. And so there's no angular dependence there. So the magnitude is R times N sub F. Okay, now, one last force. This is the friction. Okay, friction is pointing in the negative x direction. But the position vector pointing from the origin to the point of application of the force points in the plus x direction. So since these things are 180 degrees apart, and the sine of 180 is 0, that means that the force of friction causes no torque on this system. Okay? So if we sum up the three torques that we do have, obeying superposition here, we've got 0 is equal to R times NF minus R times NW minus RMG times sine of 135 degrees. Okay? Now, in that expression, R appears in every term, and so I can cancel it out. So now I have 0 is equal to mg minus nw minus mg sine of 135. My goal here was to solve for the normal forces. So if I add n sub w to both sides, I can see that n sub w is going to equal to mg times 1 minus sine of 135 degrees. And the sine of 135 degrees is root 2 over 2. So that means that n sub w is equal to mg times 1 minus root 2 over 2. Okay. Well, I hope that simple torque example from statics made sense to you and you understood it. Let me know if you have any questions, and I'll see you in class.